This video is on irregularities of ionization energy within a period. So this should be short and sweet, but it is the continuing discussion of ionization energy, but with a few exceptions to the rule that we have learned. Okay, so previously we learned that ionization energy is defined as the energy required to remove an electron. We talked about what things affect ionization energy, things like energy level, distance from the nucleus, and Zeph. We also learned the general trend is that it increases up a group, and that's because the electrons are closer to the nucleus, and it increases to the right of the periodic table because the Zeph is higher. A higher Zeph means a stronger attraction to the nucleus and thus harder to remove. So, but we know that there are a few exceptions to this, or a few irregularities, and so that's our discussion for today. So the first example is the ionization energy discussion of beryllium, who resides here, and boron, who resides, well, close to there. So based on this general trend, you would likely hypothesize that boron has a higher ionization energy than beryllium does. And you'll notice that from statistical data that is actually opposite to what we would have predicted. So the question is why? Okay, why is it actually harder to remove beryllium's electron than it is to remove boron's? And it actually has to do with something we've talked about before, and looking at their electron configurations. So if we look at beryllium versus boron, okay, so by removing, I wonder what the best way is for me to do this. I'll just color code it a different color. So, okay, if we were to take beryllium's electrons, we would be taking this one, right? That would give us a configuration of 1s to 2s1, okay, and that requires, apparently, according to our data, 899 kilojoules of energy. Now, if I were to take boron's last valence electron, then that would leave me with this configuration. Okay, and that takes 801 kilojoules, which is less than it takes to remove beryllium. So of course the question is why, and maybe you can see this, and it's because taking away the 2p electron gives me an ion with a I don't want to say a lower energy level because it's still level 2, but it gets rid of the 2p, right? So this is essentially gone, and the 2p sits at a slightly higher energy level than the 2s. So it's actually easier to remove boron's electron because it's just at a slightly further distance from the nucleus. Which goes against our trend. So it's important to know that exceptions exist. I don't think it's important to stress about them, but it's important to know. I will give you one more, which is nitrogen and oxygen. So again, based on my trend, nitrogen sits right here and oxygen sits right here. We would think it would be harder to take O's electron than it would be to take N's electron, but it's actually reversed. So it takes this much to remove N's, but only this much to remove O's. So again, the question is why? And so again, if we go to electron configurations, and this is something that we have definitely talked about before, and I'll do the same thing. I'll change it to red. We're talking about removing this electron versus this electron. So this time we're both removing them from a 2p, but with O, the removal of the electron gives a half full p sublevel. And we haven't really so much talked about this with P, but we talked about it with D. And remember, there were exceptions to the electron configurations with the half-filled and the completely filled D. Well, the same idea kind of applies when we're talking about removing an electron, because if we give it a half-full level, it's a more stable substance. So the removal of this electron gives it a half-full P sublevel, which brings stability. And because it brings stability to the then ion, it's just ever so slightly easier to remove than removing nitrogen's electron. And again, that's because if we took nitrogen's electron here, right, we're actually taking away the stability because it would have had a half-filled level, and then we remove that electron to kind of disturb that stability that had been there, and so that's why it takes slightly more energy. Again, we're talking not a lot, right? Just a slight difference in energy. So again, is it important to know that these irregularities exist? Yes. Is it important to attempt to memorize every single one? No. It's just important that you know that there are some exceptions to the rule. The last thing on your note paper for this chapter is the electron configuration of ions, which we have already discussed, but it never hurts to see it again. So we talk about anions, where we would add an electron to the lowest unfilled in level, okay, energy level. So, a super common example is fluorine. So when we give it an electron to make it F minus, of course, the second energy level is not full, and so we stick it in the second energy level to complete the p orbital. That's almost common sense. We've seen that before. You would never put it in the 3p or the 4s or something like that. It's going to go in the next available orbital. And then cations. Whoops. Cations are the kind of the opposite in terms of the electron is removed from your highest energy level. And again, we've seen this. For some, it makes total sense, like potassium. Oh, I picked a... Okay, so there's potassium's configuration, and to turn this into potassium plus 1, we would remove the 4s electron. Right? You would never try to remove one of the core electrons because we know that takes way more energy. The only time it comes up where it's trickier than that, of course, is your transition metals. We know this is one to watch for, and it's important to know that your s electrons are lost before the D, and that's because they're in a higher energy level. So again, vanadium, for example, if vanadium was going to form let's do a +3 charge, well, we would look at regular vanadium, who has the configuration of argon plus 4s2 3d3, and what students always like to do, of course, is to remove the 3d electrons, and we now know that that's false. We would actually first remove the 4s electrons, and that's 2 of them, and we would remove the third one from the D. So vanadium plus 3 would have this as its electron configuration. Again, a review, but never hurts to hear it again.